Hello, welcome to part 3, lecture 2. This time we are going to look at interaction. So last lecture we discovered the sneaky ways of confounding variables. But what if we found that the lines in this figure here to the right were not parallel and found to be statistically significantly not parallel? This is what we call interaction. So you remember this was the last figure in our last lecture where we did not include the interaction term in the model, and this is what we obtained, which was an indication of a confounding variable. Height was confounding the effect of, or the difference between those that exercise and those that did not exercise for FVC. So here's a very quick recap. 20 people recently joined a gym. 10 had no experience and 10 had some experience doing exercises at home. We're measuring forced vital capacity on the 20 individuals, and the mean FVC was compared between the two groups. Okay, so we know what's going on. Now, in this example, you'll see here we're using the data unpaired. Okay, and then underscore I for interaction. No big surprise there. And you'll see everything else is exactly the same. Okay, that's the only difference, is that I've put an underscore I, and of course the data is a little bit different in order to show an interaction. So the procedures, same for comparing unpaired means. We have the t-test, which is the basic approach, proc GLM, where we can have the fun of introducing multiple independent variables. When we look at the results for the t-test, no surprise, when you look at the two distributions of FVC between those that don't exercise or no previous experience and those that do exercise, you can see there's a shift in the center of the distribution, which would mean the means are different and there could be a difference. And yes, the pooled variance t-test produces a significant p-value. Now, height is still positively correlated with FVC, and this is something we can see here with our linear regression, or simple linear regression of FVC with height. Nice positive linear relationship. But same here, when you look at the difference in height between the groups, there is a small difference, but it is not significantly different. As you can see up here from the F test, the probability is 0.1231. Okay, here's the fun. When we then use the GLM procedure, same as before, where we include exercise yes, no, height, and then the interaction term, if we have a peek at the interaction term p-value, oh, look at that, 0.0312. It is significant. So, oh, wow, that's exciting. What does that mean? It means that the relationship of height with FVC is different if you exercise or you don't, or if you had previous exercise or you didn't. And so now that's important. These slopes are significantly different from each other. So that's an important finding. And once again, here, if we look over here, the estimate for the interaction term, this represents the difference between the two slopes. As you can see, the equations up here have changed significantly because we're, it's a tweaked data set to show the interaction. And so, of course, all the coefficients are going to be different. But here's your graph that represents the two slopes for no exercise, and inevitably, because the slopes are significantly different from each other, they're going to intersect. Now, sometimes they won't intersect on your plot because the slopes aren't dramatically different enough to see it on your plot. So in summary, because the interaction term is significant, we must leave it in the model. The difference in mean FVC between those who exercise or who had previous exercise experience and those who do not remains not statistically significant. The interesting finding is that as height increases. Its positive association with FEC differs significantly if you have previous exercise experience or not, with a much stronger association with having previous exercise experience. And you can always have a peek at the slopes in the previous slide. Okay, let's compare and contrast with confounding. So we just saw interaction. Confounding we saw last lecture. And so let's just refresh a little. So confounding is a most important problem in observational studies. It's definitely something to consider every time you do an analysis in an observational study. It results from the complex interrelationships between the exposure and outcome. And it can lead to the overestimate or underestimate of the true association. Now, confounding occurs when two factors are associated, travel together, and the effect of one is confused with or distorted by the effect of the other. So here's some examples. Age and many age-related medical conditions, smoking, and other adverse lifestyle factors. So how do we select confounders? So selection of potential confounders must occur at the design or during the design stage. They are based on clinical experience, biological plausibility, and literature review of previous studies. And controlling for factors that are not confounders may introduce bias. So be careful of that, called an intermediate variable. Now, interaction, which is also called effect modification when you're in the epidemiology world, is essentially two or more risk factors that modify the effect of each other on the outcome. So interaction is not the same as confounding. And confounding, as we've just seen, is when one variable partly or wholly explains the relationship between the exposure and the outcome. Whereas interaction, the association between the exposure and outcome varies by levels of a third variable. Here is a nice simple graph to show you confounding, which now you guys have seen this many times, whereas for instance you have age, you have incidence rate, and you have these two wonderfully parallel lines for the exposed versus the unexposed. Of course, in interaction, you have the same setup here, age versus incidence rate, but look at, just like in our example that we use with FEC, you have the two slopes that are different enough that they actually intersect within your plot. And this, of course, of exposed versus unexposed again. So checking for interaction, effect modification should be stated a priori. So as a research hypothesis, and has to be biologically plausible. And the results should be reported separately for each level of the effect modifier, as we did in our example, with the group variable involved in the interaction. That's the effect modifier, right? Is the group variable involved in the interaction. And that is it for lecture 2 on interaction. And next up is the last lecture of part 3, just a recap on confounding.